Okay, so quiz tomorrow. Quiz tomorrow. Um, and it's going to be on paper. Okay, it's going to be printed out. I actually won't be here tomorrow. I have to apologize in advance. Oh, I've got some follow-up appointments from that episode the other day, and I made them all for one day. And with some doctors, you kind of take them when you can get them. So I'll be out tomorrow, but I'll have a hand like a paper copy of the quiz for you to take. So the graph will be right there in front of you, and you'll actually write on there, and then you'll just pass them forward, and the sub will collect them, whoever that is. And then I'll probably redistribute those to you on Friday when I return and have you grade them, because it is good to get feedback. And then I'll after the quiz, I'll have a video queued up, and you'll watch a video, right? And it might be like a manticore fighting a Pegasus or something. See who wins. No, it might be me teaching. Okay. Now on your quiz tomorrow, you'll have to do the three-step definition of continuity. That's what example 7 is. So let's review. Okay, up here. We call this the three-step definition of continuity. A function then is said to be continuous at a particular value of x equals c, if and only if the limit from the left equals the function value, which equals the limit from the right. So they all three have to exist, and they all have to equal each other, right? Makes sense in terms of the analogy of continuous if we can drive safely across the canyon, right? We need a road, we need a bridge, we need a road. But more than just needing a road, bridge, road, we need them to all be connected at the right spot. So at x equals c, they have to have the same y value. So when we do our analysis, we're going to set it up the same way every time. And look how many checks you get from this. 1, 2, 3, 4, 5, 6, 7, 8. 8 alone. So if I have you do this for 2 different x values, that's 16 checks already. And at 10 points apiece, man, if you miss all 16, you make like a negative 60. That's going to really lower your average. All right. That's just, yeah, I'm really bad at math, so that's just an arbitrary number I throw out. All right. So let's look at it. We got this graph of f of x. You'll have a graph tomorrow that I'll give you. It'll be printed on your own sheet of paper. It's obviously broken up, right? There's some discontinuities. Now, you can look at it visually and immediately tell where it's continuous and where it's not. But the justifying mathematically is something entirely different. So let's just take a look at it. Let's look at this function from -6 to 8, from x equals -6 to 8. What type of discontinuity is this at -4? It's a removable point discontinuity. Very good. Does the general limit exist there? The general limit does exist. Yeah. Notice that there's no bridge. It's not even defined anywhere else. So that's a hole, right? Now, if I were asking you, like I am on part A, to go through the three-step definition, you don't say f is not continuous at x equals -4 because it's got a hole there. The hole is a consequence of how it's not continuous. It's not the reason, okay? What type of discontinuity do we have here at x equals 1? A jump. Is that removable or non-removable? Non-removable jump. And for that, we would say at x equals 1. We could say that f has a hole at the coordinate -4, 2. 2 being the limit value, right? Not the function value. But for jumps and vertical asymptotes, we just say at x equals, okay? What type of discontinuity do we have at x equals 6? That's another hole, right? Okay, it's not a jump, even though the bridge is defined here, and you might seemingly think that you jump down and then jump back up. That's still a hole because all we got to do to make it continuous is plug the hole, right? So f would have a hole at the coordinate 6, 5, and it has a function value of 2, okay? So we already know in advance where it's continuous, where it's not. But to put the argument together, something entirely different. So let's look at x equals -4. First thing that you're going to do on a test or a quiz or in life in general is to get your 3 pieces of analysis set up, all right? Because you're going to be focusing on the notation. So here we go. That's too thick. Let's see. Here we go. The limit, LIM, underneath there as x approaches -4 from the left. So try to write that contained underneath the LIM. If it bleeds out a little bit, if it goes out a little bit past the M, not a horrible sin, but it should be contained underneath there. And then again, back on the same level as the limit, we put f of x. Memorize that, get that piece down, got it. So that's the wrote in. And then leave a little space, and then we put f of -4, that's the bridge. And then leave a little space, the limit as x goes to -4, this time from the right, of f of x. That's the wrote out. You don't have to label it, wrote in, bridge, wrote out, but you can, if it helps you, right above there. All right, so tomorrow, this would be a check, and a check. All right, so far so good? All right. Now, eventually we're going to have equations. And so we'll evaluate this stuff from equations. But right now and tomorrow in the quiz, you'll have a graph. So to evaluate the limit from the left to -4, we just go to the graph and we're like, okay, from the left of -4, it's approaching the open circle, which is at 2. Okay, so that's 2. The limit from the right is also 2. And the function value is what? Yeah, dne. So notice the limit from the right is also 2. I could see that when I was over there. And there is no function value. So you could put dne, which means does not exist, or undefined. Technically, undefined for a function value is better than dne, but dne is okay. Okay. I made a meme this morning. I don't know if you can see it. I'm kind of proud of it. But remember, things cannot exist for a lot of different reasons. So I told you my calculus class has this mantra like, when in doubt, dne. And I said, but don't be in doubt. So, you could say, I don't know. But what's the better way to say I don't know? dne, right? So there you go. Fancy. What? Yeah, that's what's up there, right? Well, no, I mean, so regular poo is IDK, and then fancy poo is dne. Anyway, see, a boomer making a math meme. Pretty good, huh? I don't know. Well, because the Drake format is like it's wrong and then it's right. This one is it's correct, but it's a better form of correct. Right? Am I right? Right. Right. One does not simply just use the Drake format. All right. That's an older meme. Okay. Now, you're going to get a check for this, a check for this, and a check for this. Now we have to answer the question. There's still 2 more checks out there. It's not continuous, obviously. So you could say that it's not continuous and then tell me why, the justification, or you could justify and then say, so it's not continuous. What would you say here? Since 2 does not equal dne. That's technically correct. I wouldn't count off for that. 2, in fact, does not equal dne, right? Because 2 is an actual existing number and dne is not existent. So that's technically correct, but it's not the best phrasing, right? So again, here's what we want to say. If it's not continuous, if any one of them or more fails to exist, or any 2 of them exist but are not equal to each other, okay? So rather than saying 2 doesn't equal dne, let's just cite the dne, okay? So, and again, you could justify in the front end. So it would look like this: since, or because, whatever you want to say, f of -4 does not exist. And we're writing it out now because it's kind of like a justification, right? That would be the justification. Justification, if it says to justify, just kind of give you a definition of what that means. That means to use some type of mathematical evidence that you've already collected, combined with some words, okay? A justification is mathematical evidence in a sentence, all right? So since f of -4 does not exist, that's a check. Well, I already gave it to you, sorry. Comma, and now you answer the question. Do we just say not continuous, or it is not continuous? Not x, f, the function, right? F or f of x. The name of the function is f. So if you just want to write f, that's fine. F is not continuous. Good. And then we state where at x equals -4. Boom. Now, because of sentence structure, right? Adverbial clauses, that's what the sentence is. It's an adverbial clause. Adverbs or adverbial clauses can go pretty much anywhere in the sentence. So you could flip the word order around. You could say F is not continuous at X equals -4, comma, since F of -4 does not exist. Does that make sense? So however you want to do it. Now, usually I put the since part first because that's kind of the sequence of your logic, right? You get the evidence, you compare the evidence, you're like, oh, that doesn't exist. And now you have the conclusion. But sentence structure can work either way. All right, now, here's what I would expect you to do. Now that we have our answer and everything is buttoned up, we're getting full credit, let's pretend we don't know what the graph is. If you just looked at this information, would you be able to conclude the type of discontinuity F has at X equals -4? Yes. Okay. What type would there be? A hole. And how would we know it's a hole? Because what? Right. There you go. That's what you need to understand. The two outsides are the same, right? The two one-sided limits are the same. So the general limit exists, but the middle piece, the bridge, is different. I like that. It could be either non-existent or existent, but a different number. Okay. So the hole is not the reason for the discontinuity. Does that make sense? You don't say that F is not continuous because it has a hole there. This is why it's not continuous. But the way it's not continuous is the consequence, then there's a hole. So I might have you state that, right? F has a hole or remove point discontinuity at, and could you determine the coordinate of the hole based upon this data? Yeah. All right. It's going to be at the coordinate for the X is -4. And then the Y coordinate of the hole is always the limit value, right? Either limit value from the left or the right, or even the general limit. Yeah. Because the general limit only exists when the left and right are the same. So -4, 2. How about that? Tomorrow, I might even have you name the discontinuity. Now, of course, you could look at that and answer that one right away. But you should be able to determine it from data. Okay. So I can already envision, like on the test eventually on a free response question, you know, I just say, or even a multiple choice question. I said, given the following information without a graph, what type of discontinuity does the function have? Just based upon the data. All right. Anything else that we can do to this one? Squeeze some more good math knowledge and commentary out of it? Oh, I'm sorry. Okay. Oxygenating your brain for the next problem. That's what a good yawn is. All right. At X equals 1, here's what I want you to do. I want you to do this one now again on your own. If you needed a little help getting started on the notation, we just did that. Go ahead now and do the exact same thing at X equals 1. I'm going to pause the video and someone can remind me. Hopefully I'll remember, but to restart the video. Go. All right. So at X equals 1, first step, set up your machinery, if you will. Okay. I'm going to get rid of this page stuff because we're going to need the space. It's in the way. Right. Oh, thank you, Brady. Thank you. All right. So at X equals 1. Yeah, I did already. I did. Thank you for the reminder, though. All right. So we set it up. The limit. Whoa. The limit as X approaches 1 from the left of F. Leave a space, F of 1. Leave a space. The limit as X goes to 1 from the right of F. Okay. Check, check, check. It's all or nothing on the notation. Again, remember that the input for the function value, the 1, goes inside the parentheses. The input for the limits goes beneath the limit. Don't write the limit as X goes to 1 from the left of F of 1. Don't put it in there twice. That would be incorrect. Okay. All right. So now we go back and we evaluate it. What's the limit from the left of 1? Well, we're approaching the Y value of 4. Check. What's f of 1? Oh, I see a dot. That's the 0.1 comma 4. So that's the function value. Oops. Oops. There we go. Check. And then what's the limit from the right of 1? -2. Okay. Now, again, what Brady was doing here is he was already putting equal signs here. So like here and then not equals and here and not, don't do that. That makes it look too busy, too cluttered. You're going to save that for the end. All right. This is still the data gathering phase. All right. So you basically have 3 columns. All right. Now you can either answer the question or give the justification. Instead of using the word since this time, I'm just going to write the word because it's actually technically more correct grammatically. Since is usually supposed to be not just consequential, but in terms of time. But because would be consequently, or consequently, right? It would be another good word. Because 4 does not equal -2. So in this case, they all exist, but 2 of them are not equal. Now, when I say 4 doesn't equal -2, I'm referring to the numbers directly above. So it's not just like a random thing, right? You can't just say because 7 doesn't equal 48, right? That's a true statement, but not relevant here. 4 does not equal -2. Those numbers come from directly above. But look, which 4 am I referring to there? The left-sided limit or the function value, or does it matter? It doesn't matter in this case. So if you want to say because 4 equals 4, which does not equal -2, that's fine, but it's actually a stronger argument to leave that off, just to say 4 doesn't equal -2. And then you can take your pick of which 4. It doesn't really matter because 4 does not equal -2. That's a check, comma, and then a complete sentence. F or f of x is not continuous at x equals 1. Check. All right, now you do have the graph, but based upon the data here alone, what type of discontinuity do we have? There's a jump, okay? Because your 2 one-sided limits exist but are different. That's the definition of the jump. We don't care if the function value even exists or not, okay? So then you would say as the next one, F has a, what type is it? Non-removable or removable? Non-removable. You don't have to say that. You could just say F has a jump at x equals 1. As long as you know it's non-removable. You can still use hole in VA. That's fine. And you can just use jump instead of non-removable jump discontinuity. Okay. F has a jump at x equals 1. And that would be another check. Boom. All right. Comments, questions? How we doing? Good? Yeah. All right. Manticore, Chimera. Yeah, those are good. What did you mention yesterday, Brady? The chupacabra?
Yes.
Somebody, yeah, Long Creek chupacabras.
Seagulls.
Seagulls.
The specific picture of a hydra.
Oh, a hydra. Yeah, that's a cute one, right? The cute, not the mighty hydra, but the darling hydra or the adorable hydra.
I would like to just see a costume with like
Right?
3 poles and just heads on them.
All right, here we go. At x equals 6, we're going to do this one together. Step 1, notation, notation, notation. No notation? No points. Very good. So we get the limit as x approaches 6 from the left of f, space, f of 6, space, or tab over, right? The limit as x goes to 6 from the right of f. Check, 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 right? All the way across. Check, check, check. All right, now we come back and we evaluate. The limit from the left of 6 is what? 5. The limit from the right of 6 is 5 también. And what is the function value at 6? 2. So that should be an easy thing to do from the graph, right? 5, 2, 5. Check, check, check. Check, check, check. All right. And now the justification, right? Because 5 ain't 2, check. F is not continuous. Period? No. At X equals 6. Good. If you leave off any of that, you're going to lose the check. So it's fun to put checks, right? Check, 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 check. Microphone check, check, check. Roger, check, check, check. All right. Now, again, pretend we don't have the graph. Just pretend, right? Based upon the data and the data alone, can you tell me what type of discontinuity we have? There's a hole, right? And there's a hole because two outsides are the same and the middle is different. Yeah, I like that. So the general limit exists, but the function value, which does exist, is something different, okay? So then F has a hole at X equals, or do we write this one as an ordered pair? Ordered pair, 6, 5. Check. Right? I might ask you for this too on each one of them. If it exists, find the general limit. If it exists. Does the general limit exist here at X equals 6? Yes. What is it? 5. Okay, boom. Let's come back here to 1. Does the general limit exist at 1? The limit from the left is 4. The limit from the right is -2. Does 4 equal negative? No. So it would be what? DNE, right? So remember, the general limit only exists if the two one-sided limits exist and are the same. And then let's come back here to -4. Would the general limit exist?
Yes.
Yes. Without the plus and minus, yes, and it would be 2. So there's another. So man, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 checks apiece. That would be kind of perfect. Just give you 2, and then 10 checks, 10 checks. Now, neither one of these had vertical asymptotes, right? But vertical asymptotes are not going to be continuous. And you would say because the limit from the left does not exist, or because the limit from the left is infinity. Okay. All right. I almost put regular poo being infinity and then fancy poo DNE, but that wouldn't really make sense because infinity is only one type of DNE, right? Yeah. And it's funny then because if you don't know the answer and you put DNE, chances are you might be right. Okay. Because it's a catch-all category. All right. Comments, questions, quips, quotes, concerns, good, clean jokes. No? No? Why did the vampire move out on his wife? I'm just making this up on the fly. Because she was driving him batty. That's a good one. See, I just made that up. I'm trying to think of a Halloween joke. Yeah. Go ahead. You have a Halloween joke? Oh, okay, good. Go. What is it?
What do you call a person with no body and no nose?
Nobody knows. Nobody knows. I like that. That's good. That's good. Oh, that's fantastic. All right. We're going to move on now to piecewise functions. All right. Piecewise functions. Those are what we skipped at the end of 2.1. But now we have to know what they are. Oh, by the way, what is a witch's favorite subject in school?
Sandwich.
Spelling. Very good. Spelling. Right? Like witches spells. Yeah. What do witches put on before they go out trick-or-treating? Mascara. All right. Good segue, right? Good segue. All right. Example 8. Determine if each of the following functions are continuous at the indicated value. It says justify by sketching the graph. Holy moly. Okay. All righty. Let's look at this one here. This is the first time maybe since algebra 2 that you've seen a function like this. This is what we call a piecewise function. Okay. We've seen the graph of piecewise functions. That's what these are. Okay. But this would be the equation of a piecewise function. So we start with the open brace And as I mentioned yesterday, it's kind of like a little template for a math program. This says if x is less than or equal to 1, use the parabola. Otherwise, when x is greater than 1, use the radical function. Okay. So there can't be any overlap. It doesn't have to be defined everywhere, but there can't be an overlapping defined interval. Otherwise, it won't pass the vertical line test. So this is kind of like a manticore, right? Which is part, what do we say, part lion and part dragon. This one is part parabola, part radical, right? And this one switches at x equals 1. So the way we're going to do this one is we're going to generate a graph. Now, ultimately, what we're working towards is to answer the question without the graph, just by looking at the equation and doing our analysis and determining, in this case, if it's continuous at 1. But we need to review how to sketch parent functions, and we need to know how to sketch piecewise functions when we put them together. So here's what we're going to do. Let's go ahead and work on the individual pieces alone, okay? Let's look at the piece when its x is less than or equal to 1, okay? This is just me going off to the side. If I were just looking at y equals x squared plus 2x minus 3, what can you tell me about that function? Louder. One at a time when you all speak. Opens up, and it's a what that opens up? A parabola. Good. It's a parabola that opens up. Can we find the x-intercepts where it crosses the x-axis? Yes. How do we do that? We factor it, right? So I'm going to go ahead and set it equal to 0 so I can find the roots, right? And this factors into x plus 3, x minus 1, I believe, right? 3 minus 1 is 2. Yeah. And so remember, we can use the factor theorem now. We don't have to set each factor equal to 0 and solve algebraically. We can use the factor theorem, which says, remember, if you know a root, you know a factor. If you know a factor, you know a root. And of course, if you know a root, then you know a factor. So if x plus 3 is the factor, what's the corresponding root? X equals -3. And by the way, if -3 is the root, what's the corresponding factor? X plus 3. If x minus 1 is the factor, what's the corresponding root? X equals 1. Okay, now let's go ahead and sketch that dude. Just off to the side, here's -1, -2, -3. Here's +1. Those are the x-intercepts, and it opens up. So looking good. There you go. So there's that function by itself. Excellent, excellent. Yes, yes. Yeah, all right. Yes, very good. Now let's look at the other piece. Let's look at the piece x is greater than 1. Set it equal to y. Y equals 2 square root of x minus 1. What's the parent function for this fella? The first one belonged to the family of x squared, parabolas. This belongs to the family that is the radical. Very good. Let's come up here and review the radical function. Bless you. Y equals the square root of x. That function looks like this, okay? It starts at the origin, and then it comes out vertically, and then it goes like that. It's like half of a parabola that's fallen over. It's really reflected across the line y equals x. But you could think of the graph of x squared staying at the origin, falling over, and then losing the bottom half of it. That's kind of what it looks like. All right. So what transformations happen here then? What would the 2 do in front of this equation to the graph? If it's multiplied in the front, it's a vertical stretch by a factor of 2. That's just going to make it a little bit steeper. It's still going to come out of the origin, but a little bit steeper. But what does the x minus 1 do? That's important. Shifts it to the right 1 unit. It's inside, opposite of what appears. So here's what this graph looks like. Sketch your x and y axis. I call this point at the origin, I call it the genesis point, okay, for lack of a better word. It's the starting point for the graph. The domain doesn't live to the left of it. That genesis point was at the origin. I'm going to follow that right 1 unit, And now I'm going to draw it a little bit steeper. So there it is. That's what that graph looks like. Okay. Now, here's what we do with the piecewise function. Just like Dr. Frankenstein did when he was creating his monster, or when Dr. Susselberry was doing when he created his manticore. I just made that name up. We're going to combine the pieces of these two functions to make one brand new monster function. Well, remember, Elmo and Grover are monsters as well. So not all monsters are mean. And I did tell you the joke yesterday, which I still like. I still think about it. Why do monsters not eat ghosts, right? Because
They're like ghost intolerant.
they taste like sheep, right?
Oh,
Okay, yeah.
they're like ghost intolerant.
Oh, that's good too. They're like ghost intolerant. You got a career in Halloween joke writing, Brady. All right, let's combine them. All right, let's combine them. So here's how you sketch a piecewise function. The most important point on this graph of the combined is what? X equals 1. Very good. Why? Well, kind of. That's where it does what?
That's where it switches.
Switches. That's where it switches from parabola to radical. Right. So let's go ahead and mark that right there. Boom. 1. Okay. Now, at 1 and to the left of 1, we're using senior parabola. So let's come up here and highlight that. Do I know what that graph looks like on that interval? Yeah. Actually, let me trace over it with I don't know what color looks good. Let's see. Purple? Okay. Or that whatever this is. It's going to look like this. And then I'm going to stop right there on the x-axis, yeah? Okay. So I'm going to use that much of it. And then for the radical function, I'm only using it to the right of 1. So that's just this piece here. So if I trace that out, I'm going to put an open circle here now and trace over it. So now all I got to do is combine the two results. So here we go. Here's what our final graph looks like. Come over here to -3, because that's an important point still. And the parabola then is going to come down. And then it's going to stop right there at 1. Now the other function picks up at 1, 0 with an open circle. Do I need to put an open circle around that solid dot? No. Only one of them can claim it. They actually meet up at the same place, but only one of them can claim it, and then it goes like that. Let me see if I can draw the parabola a little bit better, because it's kind of cool what it does. Comes down. Now, I'm kind of picky. I'm gonna draw it a little shallower. There we go. I wanted to show kind of that how it's connected. It is connected at 1, 0, isn't it? But is it connected smoothly? No, there's kind of like a little sharp point there, right? The slopes aren't the same where they meet. In calculus, we say that it's continuous there, but not differentiable. So anyway, there it is. There's our manticore, right? So now we can answer the question with ease, right? Let's go ahead and set up our machinery. This is the graph of f of x. Let's label it. So here we go. The limit as x goes to 1 from the left of f of 1, and the limit as x goes to 1 from the right of f. Well, now that we have the graph, it's a piece of cake. They're all equal to what? Road Bridge Road. They're all equal to what? No, at x equals 1. 0, right? The limit from the left of 1 hits the x-axis, 0. F of 1 is 0. The limit from the right is 0, okay? Now, here's all we have to say. Since, or because, 0 equals 0 equals 0, comma, f is continuous at x equals 1. Do I need all three of those since 0 equals 0 equals 0? Yes, if it's continuous, you need all three of them, because you're saying road equals bridge equals road. And because they're evaluated up above, you can refer to those expressions by their numerical equivalent. If it is continuous, you need all three of them. Since 0 equals 0 equals 0. Since road, bridge, road are all the same, road, bridge, road, we could drive across, we can do it carefully, but we could also do it kind of with reckless abandon now because we're going to make it. Right? F is continuous at x equals 1. So we're not going to have any time for anything else, but this is enough for the quiz. Tomorrow, I'll have a video and I'm going to show you how we can answer this question without sketching the graph. Okay. It's going to be a lot quicker. Not as fulfilling, but it'll be a lot quicker. And if we can get it done more quickly and efficiently, that saves more time for more math problems. All right. Y'all have a great day. The quiz tomorrow should be fun. Yeah. See y'all on Friday.